Уважаемые зрители, уважаемая аудитория, сегодня будет интересный разговор с японским ученым Теуро Оно, физиком из Киотского университета, который у нас в ДВФУ возглавляет лабораторию спин-орбитроники, которая была создана в этом году. Я бы хотел вкратце для начала перед нашей беседой рассказать вам, что это за лаборатория, для чего она создана, и отметить ряд достижений нашего ведущего ученого. После этого мы с ним проведем презентацию, точнее он расскажет о своих исследованиях, в том числе здесь в ДВФУ, и мы проведем дискуссию, я буду задавать ему вопросы и будем получать ответы. Сейчас я говорю на русском, но ученый русского не знает, поэтому остальная часть будет на английском, но позже уже в записи появится перевод, то есть можно будет еще и субтитры видеть на русском языке. Я бы хотел отметить, что Теруо Оно является одним из ведущих ученых в области спинтроники и спин-орбитроники. Еще с начала 90-х годов он сделал несколько таких интересных открытий, о которых я чуть позже расскажу. Сейчас ученый возглавляет проект «Ферромагнитная спин-орбитроника», который поддержан мегагрантом правительства Российской Федерации по 220-му постановлению. В рамках этого проекта работа в ДВФУ рассчитана на 3 года, причем в случае успешной реализации возможно еще продление на 2 года. Как говорит сам профессор Теруо Оно, разработанные решения в рамках этого проекта смогут обогатить фундаментальную науку новыми открытиями и знаниями, которые позволят на 2 порядка снизить энергопотребление вычислительной техники и на 3 порядка увеличить ее быстродействие, что соответствует требованиям к будущим системам обработки больших данных и искусственного интеллекта. Дизайн принципиально новых энергоэффективных материалов важен для последующего прогресса и в мобильных телесистемах, и в вычислительной технике, и в автономных роботах. На базе лаборатории спин-орбитроники Дальневосточного федерального университета планируется реализовать полный технологический цикл от научно-исследовательской работы в сфере спинтроники и спин-орбитроники до испытаний и, возможно, даже опытного производства экспериментальных образцов трековой памяти и логических элементов для нового поколения электроники. Несколько достижений нашего ученого. В конце 90-х годов Теруо Оно был одним из первых, кто разработал и довел до практики нанотехнологические процессы для формирования магнитных наноструктур из обычных магнитных материалов. В итоге это привело к пониманию того, что магнитные и транспортные свойства таких наноструктур проявляют совершенно иные характеристики по сравнению с их объемными аналогами. В течение 10 лет ученому удалось измерить скорость доменной стенки в магнитных проводах и наблюдать магнитно-вихревое ядро в магнитных нанодисках. После этих знаковых открытий профессор продолжил сохранять научное лидерство в области магнитных наноструктур и в середине 2000-х годов инициировал исследования по взаимодействию электрического тока и намагниченности в магнитных наноструктурах, тем самым заложив основу для создания и развития спиновых наноустройств. Можно долго еще здесь говорить про исследования, про достижения. Я бы хотел еще несколько слов отметить, чем занимается сейчас Теруо Оно и что будет делаться в рамках проекта в ДВФУ. Сейчас Теруо Оно развивает направление, в рамках которого для развития явлений спинтроники электронам добавляется орбитальная степень свободы, тем самым формируя новую область, которая называется спин-орбитроникой. И лаборатория, которую он возглавляет ДВФУ, это первая лаборатория по такому направлению исследований в России. Как ожидается, исследования спин-орбитронных систем позволят в ближайшем будущем разработать высокоскоростные и энергоэффективные спин-электронные устройства. В частности, ученый исследовал возможность расширения спектра материалов для спинтроники от обычных ферромагнетиков до антиферромагнетиков и ферримагнетиков. Он продемонстрировал, что намагничиванием в антиферромагнетиках и ферримагнетиках можно эффективно управлять с помощью спин-орбитального взаимодействия, индуцированного слоем тяжелого металла, находящегося в контакте с магнитным слоем. Я бы сейчас хотел предоставить слово для презентации нашему ученому Теруо Оно. Teruo, please start your presentation. You can talk about yourself a little bit, and after that, present your results, please.
Okay, спасибо, Alexander. So, hello everybody. I'm Teruo Ono from Kyoto, Japan, and I'm very much happy to be here and have new application here for Eastern Federal University. Okay, today I will talk about something a bit on spintronics. Okay, so let me start this figure. So, can you imagine what this figure? So it is a photo of Google data center. And here you can see lots of servers. And so because of this kind of server, we waste huge energy. So for example, this is a forecast of electricity used in the data center. Surprisingly, it increases to 15% of total energy, electricity in the world in 2013. So apparently, we are facing energy crisis due to our information explosion. And today, I will convince you we can solve this kind of energy problem by using spintronics. Okay, so what is spintronics? So here we have an electron. As you know, electron has charge, and so you can control the motion of electron by using electric field. And nowadays, we can appreciate the electronics using this kind of electron motion by using electric field. And as well as charge, electron has another degree of freedom called spin. And this spin can be controlled by using magnetic field. And people have been developing so-called magnetics by using several magnets, like hard disk drive. And spintronics is a combination of both charge and spin. And we believe by using this combination, we can make something new devices, which is first high density, low power consumption. So this is the field of spintronics. Okay, so let me discuss about a bit the hierarchy in a computer. So here, this pyramid is a hierarchy of several kinds of memories in a computer or in a mobile phone. And this CPU in green part is called Central Processing Unit. It's a kind of our brain. And CPU can do calculation. But for calculation, the CPU needs memories. And actually, CPU do the calculation very fast in the second of nanosecond. In the order of nanosecond. So it means CPU needs very fast memories, which are like SRAM, static random access memory, or DRAM, dynamic random access memories. Okay. Then, so this is the structure of random access memory. So as you can see in this figure, RAM has so-called word line and bit line, and each intersection between word and bit lines, we have a bit. Okay, and in the case of semiconductor memory, this bit consists of capacitor. So it means we can store our data Q by accumulating electrons in this capacitor. And by using these word and bit line, you can access any of these bits, means random access. So this structure makes them very fast. Okay, but there is a severe problem, which is this kind of capacitor cannot sustain electron forever. So the electron can be leaked out of the capacitor, So it means we lose our information. And that's why a computer has to check and write in every 10 milliseconds. So it means even when the computer do not do the calculation, it's on. So we can call this kind of computer normally on computer. And this is a huge waste of energy. Okay, so question is, can we make normally a computer? The computer can working only when it's do the calculation. So the answer, of course, yes. Just use spintronics. Okay, I'd like to show you one of the biggest discovery in the field of spintronics. That's a tunneling magnet resistance effect. So here we have this kind of junction which consists of two magnetic layers separated by very thin insulator. Then when you apply a voltage, the electron can tunnel from one magnetic layer to another. And this tunneling probability depends on the magnetization alignment. That is, for parallel magnetization, it shows low resistance, while for anti-parallel magnetization, it shows high resistance. I mean, we can store information 0 or 1 depending on the high or low resistance. Okay? And furthermore, as you know, direction of magnetization is really stable. So this kind of memory can be non-volatile. Then answer is very simple. What we have to do is just replace these capacitors in semiconductor memory by magnetic tunnel junction. Then we get non-volatile, very fast reading, writing, infinite injurious memories, MRAM. Okay, so actually, MRAM has already launched. This is a photo from Samsung company. They have already do the real production of this kind of technology. And I can say this is just one example of spintronics technologies. Okay, so up to now, I'm discussing about this kind of random access memory. It's nice, but however, it's two-dimensional memory. So as I said, nowadays we are facing of the information explosion. We want to increase the information density. So from this house, we have to go metropolitan. Let's go 3-dimension. That's the next step. And before that, I'd like to introduce another discovery in the field of spintronics. It's a so-called current-induced domain wave motion. What's that? So let's imagine now we have a magnetic wire in which we have two regions. Left hand we have a rightward magnetization, and the other side we have leftward magnetization. So resulting in a transition rhythm in which the magnetization shows rotation like this. And this is called domain wave. And let's imagine what happens if we flow electric current through this wire. So electron has spin, and please believe me, there is a strong interaction between spin direction and the magnetization. So when you apply electric field to drive electron from left to right, so actually electron is now moving, but please focus on the direction of electron spin. It follows the direction of this red arrow, which is a magnetization direction. I mean, these guys are now moving with rotating. So if you know the physics, in physics there is so-called conservation law. In this case, we have to think about conservation of angular momentum. As I said, this blue guy has a change into the direction of anti-clockwise. It means the intersecting guy, red arrow, should rotate in opposite direction. Okay? So if you change the direction of red arrow into clockwise direction, so now see, oh, domain wall, this pink region is now displacing. So this gives us a very new technology. You can change the state of magnetization only using electric current, not using conventional magnetic field. So there is a possibility to make new device. Oh, actually, in 2004, we have shown this phenomenon, new phenomenon, can be happen. Actually, this is a picture of such kind of experiment. Okay, it's happened. Then, very smart guy, Stuart Parkin of IBM, has proposed new device, new three-dimensional storage. So in which he proposed to store our information in the direction of these domains. And let's move these information back and forth just by injecting electric current into this nanowire back and forth. And then this kind of device can have huge capacity of hard disk drive and the same reliability of performance of solid-state memory like DRAM, flash, or SRAM. So this is a really dreaming device. But of course, there is some problems to realize such kind of new devices. Here's the first problem. First problem, I think this is the most serious problem to realize this device because we store our information in domain wall. We have to control the position of domain wall very precisely. And Stuart proposed to control the position by making artificial structure in the device like this. It's nice work, but it's a bit complicated. Okay, and second problem, we have to reduce the current to move a domain wall to have efficient devices. And third one, so it is a bit physics. The domain wall should be very thin because we have to increase the density. And in the textbook, you can see this domain width can be determined some material parameters. So this gives us some limit. Okay. Now, we propose new kind of three-dimensional MRAM by using artificial ferromagnet. So this is an image of our 3D MRAM. There are lots of pillars, and each pillar consists of artificial ferromagnet. Meaning, so here we have two kinds of magnets for bit storage layer and domain wall layer. Let me show how it works. So first, this is the initial state. All the magnetization directs downward like this. So now we would like to write our information. It's really simple. Just inject current into this bottom wire. Then the so-called spin orbit torque works, and this spin orbit torque can change the direction of the speed. So now we write 1 here, and simultaneously we have a domain wall in layer 3, red arrow. Okay. Then we move this domain wall upwards just injecting a current into this pillar like this. So now you move our domain wall from 3 to 9. Okay? Then you can write another information at the bottom by injecting a current into the opposite direction. So you see, again we have a switching in the bottom layer. So it creates another domain wall here, right? So by repeating these kind of things, you can write any kind of series of your information into this pillar. Okay? Then how can we read out our data? It's again simple. Again, we have a magnetic tonal junction here, by which we can read out the direction of the topmost layer magnetization. So, okay, just injecting a current again and move all the data into the topmost layer, and during this process you can read out all the data. That's a technique. So it's very simple, right? And this is the kind of benchmark. So this is a bit cost versus access time. How expensive and how fast your device. And generally, there's some trend. The faster memory is more expensive, like this. So this here described, here is a 3D NAND memory. This is a non-volatile memory with huge memory density, but really slow, and very fast memory like DRAM, SRAM. The CPU needs these guys, but as I said, these are volatile memory and they waste energy. If you do some benchmark for our new device, surprisingly, our device locates here. It has the same speed as DRAM, as fast as DRAM, while the density is almost comparable or higher than the current 3D NAND. And also, power consumption is less than 3D NAND by a factor of 100. And cost is really cheap. It's one order cheaper than current NAND technology. So, really nice device. Okay, so up to now, I'm talking about spintronics, and now I will discuss about ferry magnet, which is our target in this main grant. Okay, I hope you know ferromagnet, so in which lots of spins there, and in ferromagnet, all the spins align in the same direction like this, and makes so-called magnetization. The magnetization is a vector. It's a direction of spins. And this magnetization shows this kind of rotation. We call it precession due to the magnetic field. And this precession usually gives us a frequency of gigahertz. It's a 10 to 9 hertz. It means if you use ferromagnet, you can operate the device in nanoseconds. That's a limitation of ferromagnet. But in nature, we have another type of magnet called antiferro. In antiferromagnet, so you can see the alternative spin alignment of magnets. And because they are completely antipolarly aligned, so there's no net magnetization. But however, because they consist of very tiny spins which couples antipolarly, there exists interaction between these two tiny spins, which gives another precession in the range of terahertz. Tera is 3 times larger than giga. It means if you use antiferromagnet in spintronics, you can create new devices with thousands higher speed. Okay, good. Let's use antiferro. And our target ferry is a kind of between in ferro and antiferro, in which we have two species A and B, and the spins of A and B couples antiferromagnetically like antiferro, but however, these guys have different amplitude of spin momentum. That means, although they have antiparallel arrangements, in total there exists some magnetization. So it means we can control this total magnetization by using external field. And this gives us the precession frequency in gigahertz, because this is very similar to the ferromagnet. However, as I mentioned, there are also strong coupling between these tiny guys, which give us the terahertz frequency. So you can use both frequency, gigahertz and terahertz. That's why we are really interested in these new materials. Okay, let me show one of my works. Just measure the domain wall. Maybe you remember what the domain wall is. So we drive the domain wall by external field, and we got a very strange effect. So this is a plot of domain wall velocity as a function of temperature. Just above room temperature, we see the huge increase in domain wall velocity like this. Anyway, this is the material of the alloy of gadolinium iron cobalt. So it's kind of amorphous ferromagnet. And after some consideration, we recognize this is really new interesting physics. At this temperature, we have magnetization because this is the ferromagnet, but however, there is no angular momentum. So that's why our magnet shows the completely antiferro spin dynamics, which I mentioned really fast. That's why we got such kind of high velocity. So new discovery. So ferromagnet shows antiferro fast spin dynamics. That's really helpful to make new devices. And I'd like to mention one thing. So here, we have another special temperature in which we have zero magnetization while we have finite angular momentum. So we have two temperatures, special temperatures. Maybe by using these special mechanisms, we'll be able to make some new devices. Okay, this is a kind of summary of my talk. I've shown some three-dimensional memory and some future of fast dynamics of ferromagnets. And for a project, our target is ferromagnet. So we are considering how to do research on this new kind of magnets. The key is the following. One, there exists anti-parallel coupling in between these tiny spins. And this is a new feature. The second, they have different magnetic atoms, A and B, which give us the another space to investigate. Then, okay, this is a list of the features. Antiferromagnetic spin dynamics, it's first. And because there are two kinds of atoms, we can choose one of them. It's really nice. We can control or address one of them. And also, as I said, there exists a magnetization, then we can control the magnetic state by external magnetic field. And also, because they have two elements, there exists a net spin spin polarization. And we can tune the magnetization and angular momentum by changing a composition or temperature. And finally, as I said, there exists a special temperature, angular momentum compensation or magnetization compensation. Okay, this is the final slide on my talk, which is on our project. So, aim and task. I think most important aim and task is to produce excellent next generation young and world-leading researchers. World-leading is really important. And we want to make breakthrough in electronics. And also, to do so, we have to create very nice productive collaboration between here, FEFU, and Kyoto. And we can expect many things. I mostly desire we can discover unexpected new phenomena, and we understand the fundamental physics of it. And throughout this mega grant, we want to establish the basis of next generation electronics, and we want to our result leads to the new novel spin devices. That's all. Спасибо.
Arigatou gozaimasu. Thank you very much for your nice talk. And I have some questions to you.
Thank you.
So I'd like to know your opinion. After what time can we obtain the scientific results which can be implemented in real devices? What is your forecast?
Okay, as I said, the feature of any magnet is firstly it's really fast. So by using future result, the people can realize the new electronic devices which have the 1,000 faster speed. It's really nice. And of course, as I said, now we are proposing three-dimensional memory, which gives us a huge density with very high speed and cheap cost. So apparently, if you have this kind of new memory, so our world should change. So our mobile phone can be operated very fast, and maybe you can use your mobile phone a week without any charging. So that's a future.
How soon we will have such mobile phones?
Okay, good. Our mega grant continues next 2 years. Hopefully we can continue. Maybe we can have some nice results, basic fundamental results in 5 years. And I hope our proposed three-dimensional memory can be protected in 10 years, first generation. And after 10 years, I think we will see many proposals of new devices using our research work. I mean, our fundamental research work.
Okay, your prediction is very similar to the experts' predictions made this July. It's it was a world report about next very promising technologies, and spintronics and new memory was top 10 rated as a technology which will be produced at 2030. So in almost 9 years, we will have some real commercial production.
Yes, yes.
So it's the same as your opinion.
Because they need new kind of memory in 10
Yes.
years. That's
Of course,
why.
of course,
only,
of course.
only spintronics.
Of course. Okay. Okay. How do you like Vladivostok, and how do you like Far Eastern Federal University and this campus?
Okay. I spent my time here maybe 10 days, and I really enjoyed this city. Okay, I enjoyed very nice dishes in different countries. So here, okay, anyway, food is so important. Anyway, at least for me, it's really tasty. I love the taste here. And also, I enjoyed really aggressive driving in the city. It's really fantastic, and I'm a bit okay, afraid. Okay, in general, and okay, and the people, in this university are really nice. I very much appreciate the how to say kindness and then the passion to the physics or science in general. And actually, we had some Zoom meetings, several Zoom meetings.
Yes.
But coming here, it's much better.
Yes.
And I now feel how important for us to have this kind of face-to-face direct connection, right? And only a week, we have very nice discussions, and I had really wonderful feeling on your students. The students are really nice. They have a passion on science, and they are well educated, right? And
Thank you very much for your high estimation of the level of our students. The next question. You already said that you have been working in our laboratory for 2 weeks, about 2 weeks. So share how you assess the scientific potential of the Russian group. What your next plan, and what the new ideas to implement in the near months.
Okay, I see. As I already said, the performance level is very high. I'm really satisfied with it. And okay, next several months is we have to discuss about the new projects, of course. And I have a really nice feeling we can do that very good because, firstly, the people are really nice. Up to now, I had very nice, enjoyable discussion with every guy in your group, and it's really friendly, and they are really smart, and they understood what I want to introduce.
Okay.
And I'm nice feeling. Okay, maybe even I can be stimulated, and maybe I myself can make something new idea here.
Okay.
So I have.
What is about equipment?
Yes, equipment very nice. So there's enough kinds of microfabrication equipment, and also basic equipment for the magnetic materials.
Okay, great.
Of course, but we need more.
Yes,
we need
of course.
grants.
Yeah, because we have to develop very fast to make a memory to 2030. Yeah.
Yes.
How will the interaction between your group in Kyoto and the group from Far Eastern Federal University be built? Exchange programs planned between two universities.
Yes. Yeah, actually, as I already said, I had such a good feeling, and I now recognize the importance of the direct communication. So I'm very much welcome to have young researchers here into Kyoto.
Okay,
and
great.
we can collaborate together with, and we can make new things. Yes.
Okay, thank you very much. Я бы хотел поблагодарить профессора Теуро Оно за эту прекрасную лекцию и дискуссию, которую мы провели. Конечно, было бы здорово, если бы еще у аудитории была возможность задать некоторые вопросы, но формат этого не позволяет. Большое спасибо, что присоединились к нашей дискуссии, посмотрели лекцию. Надеюсь, у вас появился интерес к этому направлению. Мы всегда рады ответить на любые вопросы. И welcome to our new laboratory of spin-orbitronics, which leader is here, is Теуро Оно. Thank you very much.
Спасибо.